Today, I'm going to be taking you through some of the features on the ocean floor. We're going to be doing it as if we're approaching the ocean from the land, and that means that we need to start out with some land. So just get some rugged land features here. Hey, look, it's the land, and then that comes down to the beach. Okay, so here's land. This is the place where you walk and stuff. This would be the beach. This is the place where you make sand castles. So we got land, we got beach, and that is on a map where the continent stops and the ocean starts. However, we're not looking at this from a geographical point of view. We're looking at this from a geological point of view, or more precisely, an oceanography point of view. So if the beach is here, that means that I might have some waves. That's fun. But basically, this is where sea level is. Now, this is the surface of the water, of course, and I've got to have the ground underneath of it. Now, this is going to be the Continental Shelf. The Continental Shelf is the shallowest part of the ocean floor. It's part of the continent. It's a gently sloping plain that's underlain by continental crust. So even though it's underwater, it's part of the continent. And it starts at the shoreline, and then it extends outwards pretty far. It could go from a few kilometers to several hundred. And the depth can reach up to 130 meters or 430 feet. So let me just draw in a typical one. Let me just have this gently slope, very gently. It's getting deeper and deeper and deeper, but it's still pretty gentle. Okay, so this is our continental shelf. I don't know. Let's just say it went out like 100 kilometers or so. Just making up a number. That's a reasonable range. And if it goes out like 100 kilometers, maybe it goes down 100 meters. So that means it is 1,000 times shallower than it is far out. That's very, very gradual. Okay, so that is your continental shelf. This is where some of the world's greatest reserves of oil and gas are. This is where there's a lot of fishing. And the continental shelf is going to run out to the continental slope. So the continental slope, let me draw a dotted line here to kind of indicate that we are in a new space. There we go. Real life coastlines don't have like borders like this. I'm just trying to do this for the sake of the illustration. Now we're going to get to a continental slope where it's about to get real. So this is going to be a lot steeper. So this is the Continental Slope. Okay, so the Continental Slope is the true edge of the continent. Okay, so on the continent, this crust is made mostly out of granite. However, on this side of the Continental Slope, the crust is mostly basalt. It's a different material. It's denser. It makes it sink down lower. That's why the oceans are deep and the continents rise up. So the depth can increase up to 10 kilometers, to 10,000 meters. So let me see. Yeah, I can fit that down there. So 10,000 meters deep. Yeah, that's pretty far. So depending on where you are on the continental slope, there may be a canyon that got cut into this. It would be kind of difficult to illustrate that in profile, but I think that there's probably a good illustration of that in the textbook for you to see. All right, so let's pick this up downward just a little bit. So let me see if I can continue this semi-logically. Okay. So continuing on like this, we've got our continental slope that is leading us down quite far. Now, ordinarily, this continental slope might have a, sharp edge at the bottom, but in fact, there's a lot of erosion that carries sediments down the continental slope, and that means that a whole bunch gets built up here. And so you end up with this much more gradual thing here. It's not, the hard stop. It kind of slopes off more gradually. And this is called the Continental Rise. Okay, so Continental Shelf heads down the Continental Slope, and all the erosion that washes sediments down the Continental Slope collects at the bottom, and that is called the Continental Rise. And below here, past the Continental Rise, we've got the flattest, widest, largest place on the planet, the Abyssal Plains. Okay, so the Abyssal Plains are blanketed by thick accumulations of fine mud. They are the flattest places on the earth. And they can have deep sea trenches in them as well. So let me see if I can move this illustration over a bit and give you a trench also. Oops. I almost had it. See, this is why real shows have animation. So the Abyssal Plains, like I said, it's the widest, flattest regions in the world. Now, let's say I've got one oceanic plate here and another oceanic plate here. Okay, so here's the image. The plates are coming together, they converge, and then one of them will subduct. So the subduction causes some friction that ends up buckling them both, and you end up with that trench there. Now, obviously, I'm just demoing it with my fingers. It's not exactly quite like this, but you get these trenches that are the result of two plates converging together. One of them subducts, and the friction kind of tucks the other one under. So a deep sea trench is going to have a look kind of like that. Now, these are the deepest places in the world. The Marianas Trench is in the Pacific Ocean, and that one is 10,994 meters deep. That is 36,000 feet. That's quite a few miles deep. So they generally run parallel to the edges of the continents. Kind of like in the Pacific Ocean, the Ring of Fire, the volcanoes run along the edge of the continents. The trenches do that too, just on the ocean side. And the Pacific margins generally run to a trench because of the convergent plate boundaries there. Okay, so some other feature that you might have in the ocean, that would be a mid-ocean ridge. So clearly, if these two plates are converging, that means that they're moving that way. So let me scoot over a little bit more because the next feature involves a divergent boundary, and I need to make sure that I can illustrate that one. So let's move this over some. There's a trench. Okay, so if you've got a divergent boundary instead, okay, I've got another tectonic plate over here, and they're moving apart. Well, there's mantle down here. If this opens up, it's almost like a sunroof just opening up, and the magma can come out, which means that, let me close this up a little bit, there is going to be a kind of like almost like a volcanic-ish opening here as the magma underneath the surface has a place to come out when these plates diverge. And this will make a mid-ocean ridge. There is, in fact, a mountain range that is formed this way that runs through all of the oceans. It has a combined length of 70,000 kilometers. I mean, it runs all the way around the world. It's 44,000 miles long. And the Mid-Atlantic Ridge, again, mirrors the coastlines of the continents it's between. If you remember back when we were talking about continental drift, it basically traces directly between South America and Africa and North America and Europe. It's as if that is where the continents were split, and that's the scar that's left. So these mountains are usually too short to reach the surface. However, they do reach the surface in Iceland. That is one place where they reach the surface. Okay, so there is, mountain formed here, but in the center, sorry, I should have written mid-ocean ridge. Mid-ocean ridge. There you go. So in the center of this mid-ocean ridge, there is a little valley. Let's see this little valley in there. So that little valley is called a rift. And that valley could be over a kilometer deep, like more than half a mile. It's frequently the site of volcanic activity. And if there is a, exposed magma here, that can cause what's called a hydrothermal vent, which basically is a source of superheated water because of the magma nearby. The water can be up to 350 degrees Celsius, which is 660 degrees Fahrenheit. It's well above boiling, but only at normal air pressure. Way down there, under all that pressure, you can actually heat up substantially more before you boil. The water there is rich in minerals like metal sulfides and oxides. If it were accessible, maybe those minerals would be, useful as an ore, but, it's right next to magma and at the bottom of the ocean. So good luck getting that. And it's possible that some of the chemical ores on the continents were formed that way. That's also home to some really crazy life that we didn't know existed except fairly recently. Okay, so we've got some exposed, or I shouldn't say exposed, nearly exposed magma here, and that was at a divergent boundary. What if instead of being at a boundary, it was just in the middle of a plate? So here's the situation I'm describing. We've got a magma pocket. There's like a thin spot here in the crust. Now, this isn't necessarily going to come up all the way. Just comes close. What can happen is this can produce a mountain on the bottom of the ocean. Okay, so if this is your magma, this is a volcanic mountain, right? And if it's under the ocean, then it's called a seamount. On the other hand, if it is tall enough to stick out of the ocean, let me just put the water level in there so you can see it. I know that's not over the magma hotspot. Don't worry about that just yet. So if that extended out of the water, let's say this is the water level. Well, you know what that is? This is an island. And there's a lot of Pacific islands that are formed like this. They are volcanic islands. Hawaii is one example of an island like that. That's why there's an active volcano on it. So this kind of magma pocket that causes these islands to form in the ocean, this is called a hot spot. And here's what happens, okay? So if the plate's moving this way, let's just keep the plate moving that way. This magma pocket, this hot spot, formed this mountain a while ago. And then the plate drifted over, and it's now forming this one. So this one is older, and this one is younger. This one hasn't even turned into an island yet. Now, if that's true, then if we keep going to the right, we should find an even older mountain, one that the hot spot formed even before this one. So let's head over there. Let me get that way. Just doing my homemade animations here, because yeah, that's what I do. So we'd have an even older volcanic mountain that formed underwater, and it has been exposed to weather above the ocean, which means it's been eroded flat. It's now a completely underwater mountain, and the water level now covers it. Erosion above the surface has wiped it out. This is called a guyot. Guyot. Now, what's really cool about this is that while this island forms, you know, it has like a miniature one of these around it, right? There's a beach on a volcanic island, which means that there would be fish living here. There might even be coral reefs and all of the ocean life that goes with that. Well, guess what? When the island erodes, the coral reefs are still there, which means that this might actually still be surrounded by coral reefs. Now, as this continues to erode, or if the magma pressure completely disappears and then this is, just going to sink back into the ground, it can actually leave the coral reefs there. And if you have an island that is basically just made out of a ring of coral reefs that used to be around a volcanic mountain like this, that's called an atoll. The reef itself is called a barrier reef. All right, well, we only have one other thing that we need to talk about as far as the ocean floor, and that is the sediments at the bottom. So the abyssal plains are covered in some fine sediments. And these fine sediments have a couple different sources. So one source that they could have is they could just be formed directly from the seawater. You know, they could be chemical sedimentary rocks. Something else that they might be would be possibly caused by biological activity. Now, we talked about calcium carbonate as a mineral that is common in a lot of rocks. It's what limestone is made of. Calcium carbonate is also part of the shells of a lot of marine creatures. which means that eroded coral reefs could end up turning into sediment. You could end up with, skeletons of large or even microscopic creatures. Obviously, microscopic creatures, I'm not talking about like bones. I'm talking about like cell walls, might end up turning into sediments. So they could be chemically formed from seawater, biologically come from organisms that lived under the water. And the last one is they could be formed from erosion from land. So I've drawn the other side of this coast. We've crossed the entire ocean. And I know I'm not being very consistent with the water levels. I had the sea level down there to begin with. I'm not drawing things to scale. I mean, that should be obvious. So let's come back up here. We're on the Abyssal Plains. Now, just quiz yourself. Can you remember the name of this gradual ramp right here? Just as a reminder, it's made of eroded sediments from up here. Do you remember the name of that? Take a second to try to remember it before I write it down. You can pause the video if you want. So this is the Continental Rise. Continental Rise. Okay, now then there's this sharper vertical, and that has another name. See if you can remember what that is called. Pause the video. Okay, so this is the Continental Slope. Okay, now the Continental Slope leads up to this more gradual, gentle slope. And see if you can remember what that is called before I write it down. Just pause the video, remember it. So this would be the Continental Shelf. And then, of course, we just have the beach, and then there's the next continent. So, rain falls on the continent, rivers wash sediments down. Sediments end up on the continental shelf, but currents carry it down the continental slope. They form the Continental Rise, and they end up all over the Abyssal Plains. Okay, well, that is a complete tour of the ocean floor. There is no more. So, since there's nothing else in store, I guess that, I'm not sure.